Okay, so picking up where we left off in the last video, we proved that this function was on 2, and so let's take a function now that's not on 2. I've changed the function up a little bit, 2 to the x plus 1, going from all real numbers to this codomain, -10 to infinity. And so you may remember this type of function from your algebra. That's an exponential function. Actually, an exponential function that's been shifted up by 1. It's going to look something like this, and you might remember there's going to be a horizontal asymptote at 1 because it's been shifted up by 1. So you can see that the range of this function is going to be, now remember this guy is never going to touch or cross the asymptote, so it's 1 excluding the 1 to infinity. So you can see that we've got a mismatch between the range and the codomain. And so how would we verify that this function is not on 2? Well, one thing we might do is take the negation of our definition. Right? If I negate, so remember, if I negate for all, I get there exists. And if I negate there exists, I get for all. So that would mean there exists a b in B, so that for all a in A, and then the negation of f of a equals b would just be that f of a not equal to b. So if we want to verify that a function is not on 2, we have to select some number from the codomain, right, this is b, so that for all of the x values in the domain, we are never going to be able to get that y value. Let's see if we can figure out how to make that selection in our picture. In our picture, right, we've got here that the range is these values going from 1 to infinity. Right? However, the codomain, if I get a little bit different color, well, let me extend my y-axis here and then pick a little bit different color, because my codomain is -10 to infinity. Right? So the codomain is that interval. So you can see in here we've got some y values that are in the codomain but not in the range of the function, and this is where we want to make our selection. Right? That's where we want to choose some element here that is in the codomain, but right, we're never going to be able to produce any of those y values. Right? There's nothing we can plug in, there's no x value we can plug into this function that's going to give us any y value in here. We can see that in the graph. So let's pick whichever y value we like in there. We could choose, well, I guess we're going to call it a b value. We could call it a y value, it doesn't matter. Let's pick y equals -4. Right, we couldn't choose anything down here. We couldn't choose -11 or anything like that, because then it wouldn't fit in the codomain. Right, that's outside of the codomain. So let's say y equals -4, and then what we've got to show is that no matter what the x value is, right, for all the x values, we're never going to be able to plug that x value in and get -4. So we're going to do this. We're just going to take our y value that we've selected and put it into our function. Right? So remember, the function is y equals 2 to the x plus 1. Right, so if we plug in for y, negative 4, okay, well we might do a little bit of rearranging here just so we can see this a little better. If I subtract 1 from both sides, remember that the basic exponential function, 2 to the x, any number to the x, right, is always positive. Right? You can't think of any exponent that's going to make that number negative. Right? So there's no solution to this equation. There is no x value that's going to make that work. Right? And that's what we wanted to show. This has no solution for all x in the domain. Right? It doesn't matter what x is, there's going to be no solution to that. Right? So we've found a y so that actually what we showed is that this is true for all values of x, right? For all values of x. And when you went to try to solve equations like this in algebra, one thing that you did was you applied the logarithm to both sides. Right? And if you think about attempting to do that here, if you tried to solve that way, you're going to run into a problem because you're going to have the logarithm of a negative number, which you can't do. Right? So no matter how you try to solve that, you're going to find out that there is no solution, no matter what the value of x is. Okay, so that's how you prove that a function is not onto. Right? So if we wanted to make this function be onto, it's really easy. We don't have to change the function, we just have to change the codomain. We just change the codomain to match the range of the function. Right? So if this had been the codomain, then we would have been proving that the function is onto instead of not onto. So if you're ever asked to create a function that's not onto, you just have to create a mismatch between the range and the codomain. So let's do something like this. Find a function that is one-to-one but not onto. So what I would do is think of your functions from algebra. Think of your functions from algebra and think of any function that will pass the horizontal line test. One function that comes to mind is the square root of x. Right, so remember that the graph of the square root of x look like this. That is one-to-one. So I'm sorry, that does pass the horizontal line test, so it is one-to-one. And then we have to think about, well, how are we going to make that be not onto? Well, the domain of this function was 0 to infinity, and the range of this function, when you talked about it in algebra, also 0 to infinity. Right, so if you want to force this to be not onto, you just have to pick a codomain that is not equal to the range. So let's do something like this. And maybe I should have been a little bit more careful about what I said. We don't want to pick, right? We don't want to pick the codomain to be something like this, right? Because now there is a mismatch between the range and the codomain. However, if we pick this for our codomain, the function is still going to be onto. I mean, if you think about what you've done there, you've just made the you've made the, I'm sorry, I'm drawing on the x-axis. Let me go back to black. Go back to black, and then, right, so here's 1 on the y-axis. Right, so if you make this your codomain, right, you're going to be looking just at this part of the function. Right, but that function is still going to be on too, because all of these y values are going to get used. Right? All of those y values are going to get used. So what we need to do is we need to extend the codomain down here somewhere, right, where there's y values that don't get used. So I probably should have been a little bit more careful when I was saying when the range and the codomain don't match up. That is true, but if you're trying to create a function that's not one-to-one, you do have to think about how you're going to do that a little bit. So we want to make the codomain be like -1 to infinity, or -2 to infinity, or something like that. So to create a function that is 1-to-1 but not on 2, oh, let's just, well, okay, let's say square root of x, and remember you have to say from the domain, which we can use 0 to infinity, that makes sense for this function, 2, and then let's make the codomain be -3 to infinity, or something like that. Right, because now we can see, you can see -3 to infinity, there's going to be y values in here that are never going to get used. Right? Y values in there that never get used. Right, so we've got a function that's 1-to-1, we know this passes the horizontal line test, and we were sure to make the codomain, not only did it not match the range of the function, but it didn't match in a way where there were y values that are never going to be used by the function. So hopefully that makes sense. Hopefully I haven't confused you too much, but those are some of the basics of what we think about when we talk about an onto function.